I'm Lucas Cherian,
I'm Evan Simon.
and we're presenting vehicle disc brakes as our CM4 final project. So just some things we'll cover today, a brief introduction, what our idea is, how we ended up modeling it, the results we got, next steps, and finally a conclusion. During continuous braking, the efficiency of a brake decreased up to 50% over the lifetime of a car. We hope to tackle this idea by coming up with a new way to model brakes in order to better preserve the efficiency over long uses. Brakes overheating limit performance and the safety, especially during sustained braking, especially during downhill driving. During braking, kinetic energy is converted to thermal energy in the pad-disc interface. Excess heating leads to brake fade, reducing stopping efficiency and reliability. Drilled rotors improve cooling, but the optimal number of holes is not well understood. Increasing hole density reduces thermal mass while altering airflow behavior. So our idea. So here's an example of some possible hole combinations we can use for our brake rotor. We plan to drill holes into the brake rotor to lower the maximum temperature of the rotor and preserve brake efficiency. So how will we test this? We plan to use downhill braking as our standpoint, and we will simulate a car braking to maintain 40 kilometers per hour down a 7-degree hill.
Okay, so for the console modeling, so the method that we're going to use is this thing called homogenization. The thing is, if we make the holes in the brake disc small enough, as you can see, if you make the holes in the brake disc small enough, as you get to a larger and larger scale, the effect of the holes effectively gets averaged out into a material property inside the brake rotor. And since our holes are, like, if we have holes that are like on the scale of 0.1 millimeters and the brake rotor is on the scale of centimeters, then we can model the effect of the holes, how the holes become a material property. That's step one. This is what we call our fine grained simulation, where we have a small scale simulation of how the holes affect how the air flows over the disc. And then we have a large scale simulation of once we have that material property, which shows how the air flows over the disc, we can just do a parameter sweep of that material property to just get a lot of conditions of possible hole combinations. So the main thing we're going to be dealing with is something called a slip condition. So when you have air flowing over a surface, for most surfaces you have something called a no slip condition, which means that the velocity of the air is zero at the surface of the part. And we also have something called a slip condition, which is the airflow is not affected at all by the part, and it just maintains a constant velocity. Then we have something in the middle called partial slip condition, which is modeled by something that we call the slip length. It's basically saying if you were to extend this velocity profile down into the part, how long before would you get to a zero velocity at no slip condition? So the effect of a no slip condition is very bad for heat transfer, since you have a pocket of non-moving air right above the part, and air and heat doesn't travel that well through air compared to metal, so it takes much longer for the heat to conduct upward. If you have a slip condition, then the air will just be constantly taking away heat from the surface of the part, but that doesn't work because we have an actual brake rotor. So what the effect of the holes is that, like, for half of the holes for when the air is flowing over the holes, it's a slip condition, since it's just air flowing over the air. When the air is flowing over the actual part, it's a no slip condition. And since the holes are so small, we can average that out into the effect of the holes in total, which can be represented by the slip length. This is what we do for our fine grained simulation to find the effect of the density of the holes on how they affect the slip length. So that's what we do here. So if we do an array of holes which would be periodically repeating across and also down. It's basically a unit cell of holes, and we vary the size of the holes from approximately 0.05 millimeters, 0.13 millimeters. So it looks from this, it goes from something that looks like this to something that looks like this, and we have a much higher density of air versus metal in this case. And we have an inlet condition here where the air over here and here, where the air is flowing into the domain. We have outlets there and there where the air is going out. the top of the metal, like over here, and the inside of the walls is a no slip condition. Then everything else, since it's air on air, is a perfect slip condition and just be modeled like that. So after we do it, we get so here's the inlet and here's the outlet. And as we can see, the air gets constant, the boundary condition, it starts at very small, but then since we're simulating a unit cell, the actual brake rotor wouldn't be, there wouldn't actually be an inlet. So we chop off here and say this is approximately a constant boundary condition, and we can see that over here where this is basically plotting the velocity magnitude along here, which is showing like where there's a flat spot, there's holes where it goes up. Where there's a flat spot, there is no holes. It's zero velocity. Then when it goes up, it's showing the slip condition. And then since we can see the last three, since the last three are approximately the same height, we just say everything before this doesn't matter, and average the effect of these holes into the average velocity over these three holes. And that is what we did. We find the average velocity over this part of over this surface over here. Then we divide that by how much that velocity is changing as you go up, and that gives us the formula for the slip length, which is what we were trying to find from our fine grained simulation. Then we also find the effective density by the formula there, and once we do that, we get a relationship, the actual relationship between the slip length in meters and the density and the effective density of our part, which we then plug into, once our coarse grain simulation is done, we can then plug into it to find the actual physical parameters of what the slip length is compared to density.
So for our coarse grain setup, we basically took a pre-made console design of a disc brake rotor, and we applied some additional physics to it, as it wasn't quite what we needed for this project. So we added some Navier-Stokes and laminar flow, and we made sure that it would exactly fit what we need for this project. So some boundaries we used, we have, similar to before, we have an inlet where the air is coming in, and out where the air is coming out to simulate the airflow. And here we have the disc that actually spins, and that's through translational motion. And this little pad here is what's actually causing the braking and causing the heat generation from the friction. We also have an outer boundary which allows heat to flow outside of our defined area and create a more realistic standpoint of the brake itself. The wheel and the car are both going at 40 kilometers an hour to match the fine grain. So some important physics we use thermal contact as discussed before. This is basically what simulates the heat generation in the disc from braking. Heat storage, which is how the density affects the heating of the brake itself, and airflow, which is what causes the slip conditions to actually be affected. So with the slip conditions in mind here, we have to consider a parameter sweep of these variables that we talked about previously in the fine grain, and apply them to the course in order to see if our results match up. So here are some important formulas, how we got the pressure of the brakes inside the car, as well as the wheel spinning velocity for the translational motion. So after performing our parameters sweep, we received these results, which just looks like a rainbow, but it actually describes how the effective density and the slip condition here and slip length affects the temperature, which is the color on the graph. So once we have this, we can apply the previous line graph on top of it in order to show what is actually possible for our rotor brake.
Okay, so we have, here are our final results of the two things superimposed. So the first is the coarse grain simulation, which is basically varying this, which we said before, as before, is varying the slip length and the density to create all possible parameters of slip length and density, of slip length and effective density, of what the max temperature will be. And then the fine grain simulation is what's the relationship between the slip length and the effective density, which actually places us on, which actually gives us what the realistic results would be on this graph. So anything across this line is something that could actually happen based on the whole parameter, based on the whole pattern and the density that we use. Anything that's off of that line can be maybe achieved by another whole density, but it can't be achieved or another hole pattern, but it can't be achieved using our part. And we actually found a noticeable result, which was that when we increase the density, when we decrease the density, increase the amount of holes, we actually gain around a 25-degree improvement in the max temperature of the braking, max temperature of the brake rotor, which is, we think, pretty significant. And yeah.
So what are some future steps for our project? So we saw 3 big things, and the first is turbulent flow. In our model, we only use laminar flow, which is very basic and simple, and if we introduce turbulent flow, it would involve the roughness of the surface of the part, and this flow will create a more realistic and holistic view of our part. We also want to look into more different hole geometries, as right now we're just using circles, but we could use certain line shapes or spirals or any sort of combination, and also a stress analysis, as we know that lowering the density, increasing the number of holes can have a huge effect on the part's structural integrity, and could even lead to future issues with braking efficiency if it's not strong enough to handle these intense loads. So if we had more time and more money, we could definitely get these future items accomplished. So in conclusion, our results are confirmed. We do believe that our design will improve braking efficiency in cars and help preserve braking life, as well as make cars more safe moving forward.
Okay, so why we think this approach deserves more research and more funding to be able to continue it. So first is, we didn't use a simplified model for the generation. We actually simulated navigated slopes of what the actual airflow over the brake will be. And the second thing was that the benefit of the homogenized approach with the fine grain is that if we want to test different hole densities or different hole patterns, then we don't have to re-simulate the entire thing. We just have to do a new fine grain simulation, which will then create a different relationship like a different relationship on that map of total spaces that the coarse grain simulation was made, and so you don't have to simulate the whole entire thing every time. You just have to do the fine grain, and then you can just superimpose that plot on the coarse grain like we did before. And then we've shown that it works, but we also want to investigate it further to see. We're pretty sure that turbulence will increase the heat dissipated from the brake rotor, but we're not sure, so we want to investigate that effect also of the vortices inside the brake rotor and see how they affect the boundary layer of air. And we would also want to try and do a shape optimization of the hole geometry to manage to increase the slip length without lowering the density as much would be one thing we want to do. And yeah, so basically we've shown that it works, and we would like more funding to be able to investigate the effects further, to make them more accurate, and B, to be able to improve the effect from 25 degrees to maybe as high as we can go above that.
Thank you so much. If you have any questions, feel free to email us.